Thank you, Fernando. I would like to thank the organizer for having me here today, and to you all for being present. So today I'm going to be talking about renormalized volume. I will try to motivate a little bit the definition of it, as well as trying to talk about some of these problems, some finding bounds and calculating these quantities, as well as trying to discuss a little bit the techniques that come while we do that. So a simple heuristic for this whole procedure is going to be the following. We're going to have an object who's going to have an infinite volume, but we would like it still to associate a finite quantity that we will still like to call volume. So the main idea in order to do this is going to be done by the following procedure. We're going to take a compact part of our object for which we can calculate the volume. As soon as we start taking larger and larger copies, we know this quantity is going to blow up to infinity. But if we manage to understand at which rate it's going to blow up, we can hopefully subtract that quantity, which could be either, a polynomial, could be exponential, and then we could rescue a finite number. This finite number is going to depend on some choices, so we will need to make the appropriate ones for this number to have a geometric meaning for us. Just to be clear, while you can do this in a lot of general setups, I will be thinking on three-dimensional manifolds, Riemannian manifolds, where G is going to be a hyperbolic complete metric, M is going to be the interior of a compact manifold, such that the boundary is not empty with no Theorem components. So it's going to be the usual setup in which I'm going to be working. So in order for us to make a problem, we would like to understand first at which rate the volume is blowing up under this. And for that, we need some variation of volume formula that is suited to our needs. In order to do that, let me talk to you about Shapley formula. Formula is a well-known formula which states the following. For a space form in dimension n+1 with constant sectional curvature equal to k, let's take a smooth family of polyhedra parametrized by parameter t, such that the combinatorics do not change with time. So you could imagine some cube moving in Euclidean space, inside the sphere, inside hyperbolic space. And we would like to understand what is the derivative of the volume in terms of time. And Shapley formula states this is going to be equal to the following quantity. Where here the I parameter goes over codimension 2 faces f, in my example here represented by just a simple h. Theta, this is just going to be the interior dihedral angle. And W1 is going to be the codimension 2 volume of the face. So in this particular example, would just be the length of this segment. So let me there are many ways to prove such a result. Let me give you the heuristics of a proof done by Hobson, which is based in the following two observations. The first one is for m equal to 1. This is a well-known formula for all of us. In this term, volume is just going to be area. We're just going to be dealing with some polygon. And for that particular case, because of Gauss-Bonnet, we have the following formula. We have an integral version of it, which is the sectional curvature multiplied by the area is the sum of interior angles plus a constant. And just derivating this in time, you see that this formula follows easily because now codimension 2 faces are just points which have mass 1 for us.
Sorry, you're assuming that the faces are totally geometric?
Yes. Yes, we're assuming that in this case the polyhedra is totally geodesic. The second observation is that there exists a measure for dimension 2 planes in this space, which is going to be invariant for isometry. And moreover, we have the following formula. We could either calculate the volume of PT normally, let me name the planes by Q, or we could just intersect PT with Q. We could take the area of such intersection and integrate with respect to this measure. So now the argument is going to follow, but just we want to calculate this derivative of time. And before creating something here incorrect, I should say that this is up to some dimensional constant.
So I can't read. There exists what?
There exists a measure.
Oh, measure.
So we can just calculate either the full volume or the mu. Yeah, I should say that this measure was, as you go along, varying Q. So now the strategy is just to differentiate under the integral sign. So at this side, we should be obtaining C times the derivative of the volume. And this side, when we differentiate now the area, we could use the dimension 2 case that we already know. So we will have, we can decompose this as derivative in terms of the area. And now in order to compute this integral, this derivative, you could do the following construction. If here this is a phase F, we know that when we derivate the area in a particular plane up to divided by k, we should just be capturing the derivative of the angle. So if we fix a point x in F, we should be taking the integral of all possible planes that pass by x. The integral of all these angles is going to be proportional to the interior dihedral angle. And then we also need to do this for every x inside of F. When you put those two lines together, here you will obtain my term over here. But the relationship between the integral of all possible angles, I did the dihedral angle, comes also with a dimensional constant that in this case is going to be given by the previous dimensional constant divided by mk. So when you put all of this together, you should be recovering Shapley's formula over here. We're interested in this particular formula because of the following. If we were going to integrate the mean curvature over the boundary of this polyhedra, this will correspond to the following sum, where here, if you imagine this is a codimension 2 phase, you could imagine that both planes are coming here totally geodesic, and all your mean curvature is included in this phase. And this is the volume that you will have. This is useful because now when you derivate this, this tells you in a heuristic that, in general, the derivative of the volume should have a integral of the derivative of the mean curvature inside. That just comes because when you derivate this in time, you will have product rule, and one of the terms you're getting there is exactly the one you're capturing here. So then let me quote the following theorem, which is a smooth Shapley formula states the following. Let me take m plus 1 a Einstein manifold with a metric such that the Ricci tensor is a fixed constant times the metric with constant scalar curvature equal to S, and H a smooth variation of G by Einstein metrics. Then you have the following formula for the variation of volume. Where in here, remember we were before dealing with sectional curvature, that we don't have it constant anymore. We have constant scalar curvature, and this is what mk is going to convert in that case. This is your derivative of volume. Here is the h prime term by the previous heuristic, and this term of the variation is the variation of your metric restricted to the boundary inner product with the second fundamental form, where here we're taking inner product of symmetric tensors.
So excuse me, so
sure.
By smooth metric, you mean that the family of variation are all Einstein?
Yes.
But if the Einstein metric say itself is kind of stable guy, then there's the only one. So
well, you could, for example, as in this case, when you are moving a polyhedra inside a fixed space form, that value is changing. And in fact, when you have this type of hyperbolic metric, you have a whole parameter space of metric constant sectional curvature -1 that they are not necessarily equivalent with each other. Okay, so now we understand how volume is behaving.
So sorry, the
sure.
H prime, I mean, if you're, how are the angles, how do the angles appear in that formula? Because H prime, isn't it 0? I mean, you have to somehow get the discrete approach.
Oh, yeah, I mean, that's the comment I'm doing up here. Notice, like, first of all, this is just a smooth version. So here I'm assuming that the boundary of the object I'm looking at is a smooth object. In the previous object was a discrete one in which, yeah, this is a smooth version of it. So now that we understand how volume behaves, I'm going to spoil a little bit and tell you ahead one of the correction terms and then analyze it here. So now the picture you should imagine, we are back to the hyperbolic three-dimensional case, is that we have m with an infinite n. We have n here, which is a convex domain. And we're measuring here the mean curvature with the normal vector pointing out inwards. If we define now this quantity, we can take ns, which is points at distance s from n. If you were going to derivate the W volume of ns, you should obtain the following formula. all of this is just applying your smooth variational formula. And this factor has just the right constant such that you have a simple formula like that.
What are terms? What is delta?
Sure.
Delta.
Sorry, here delta, I'm interchanging delta of any quantity, but just its derivative in terms of the parameter. It's particular that in this equidistant foliation, hard to see that the variation of the metric comes in terms of the second fundamental form, and the variation of the second fundamental form comes in terms of the metric plus a third fundamental form where, recall, if the second fundamental form is defined in terms of the metric at the shape operator, you could define this other symmetric tensor by doing the following. So when you use this entity in this particular case, this factor is going to reduce to 1/2 integral over the boundary of minus the Gaussian curvature of the metric at time s. Just an exercise of replacing these two variations here and seeing what simplifies to. Well, this integral is going to be, without the minus sign, is 2 pi Euler characteristic. So all this value is going to be equal, by Gauss-Bonnet, to minus pi Euler characteristic of the boundary of n. This is going to be a fixed number, negative number. So we know that this function is growing up as a polynomial. In particular, we will be able to define the following. If we have an equidistant foliation, we could define its W volume as the W volume at any level plus pi s Euler characteristic of n. And notice, like now, because of the calculation before, this number does not depend on s. So with this, we end the renormalization part of calculating this quantity. We understand now how to rescue the finite number.
And we assume that the foliation, there are no focal points, that the whole thing
exactly.
is smooth and whatnot.
Yes, we need to assume that they are all focal points, which can be assured, for example, if the original submanifold has convex boundary. But yeah, as Andrea is pointing out, there is a detail here about how to assure that this construction could be done. And moreover, even when the construction can be done, we could have multiple different versions of it. So we need to pick one in order to have a well-defined number. So I'm going to talk about that next. So let me talk about visual metrics. Here, let me just take the ball model for three-dimensional hyperbolic space, which has a boundary at infinity given by S2. All the isometries of H3 are just going to be conformal maps acting in S2. So it's quite hard for us to, just out of that, to put a metric in S2 that behaves well with respect to this group of isometries, because the conformal maps will in general change our notion of distances. A key observation is that if we're going to pick the isometries that fix the origin, now we're dealing with the group of isometries of S2. So we're able to define to have a well-defined metric inside here of S2. Given that, we are able to do the following construction. Pick a point in the boundary of hyperbolic space by C and pick an interior point X. You're going to have many, but at least pick one of them, of isometries of H3 that are going to fix C but are going to send x to the origin. And now when doing that, you could define the visual metric at C as just the pullback of this map of the wrong metric at C. Because this map is in general conformal, we know that this is just going to be a constant, which depends in x and c, times the already wrong metric that we have at c. It's called visual because you could imagine that as you're declaring x, your point of origin, your point of observation, this is how in size you see the point c. And in particular, as x goes closer and closer to c, you will see the metric blowing up at that particular point.
You said c is a constant.
Sorry?
You said that c is a constant.
For that map, yes, but this you could define a metric by varying both x and c. In particular, if you have rho, a conformal metric at C, meaning conformal to the metric in S2, you could define the following set. You look at all the points such that when you look to your particular metric at C, this coincides with your visual metric. It's a nice exercise to see that this is a orosphere, meaning it's going to be a Euclidean sphere, which is going to be tangent at C. So all the points in that little sphere are going to give you the same conformal factor here to multiply, or in particular the same metric at that point in that particular point of S2. And for this, it is important that you fix C in order to calculate this. This is useful because now we could do the following procedure. So assume, I'm going to imagine that this is inside, I have an object inside H3. I have a point C. And I could now take a point in the complement of the closure. So I know there is going to be a little orosphere that doesn't touch my particular set here, C. So then there is going to be a biggest orosphere with such a property. So in a similar way, you could define visual metrics for objects at points that need to be in the complement of the closure. This is useful because now we can translate embedded or parametrized objects inside hyperbolic space to conformal metrics of S2, which are a lot more easier to understand. The problem is that this construction, if we would like to use it for renormalized volume, we'll need a sort of inverse. Right now, with this short explanation, we only know how, given an object, how to more or less construct this metric. But if I have a special metric, we don't know per se we have an embedded object realizing that given metric. Such construction could be, for example, done by Epstein as follows. Again, here imagine that you have an S2. You're going to have an open set U, a rho, a conformal metric in U. Finding an inverse of this type of construction means the following. This function rho, which we're assuming to be defined, is going to determine an orosphere at each point. So for example, something like this. So finding an object that will give me back that metric is the same as finding an enveloping map for those sort of spheres, because of the definition of first point of contact.
Sorry, Franco, could you remind me that I'll give the conformal metric on you determine the horosphere? You explained that, but you know.
Sure. It's just because when you look at all the points, all the base points that will give you the same metric, that set is an orosphere. So it doesn't matter which point of the orosphere you pick, that's going to give you the same metric. And the good point is that once you fix C and take all the possible orospheres, you're capturing all the possible metrics. So all that you do is you see what Roy is telling you how to measure your angles. Then there's going to be a unique orosphere that measures the distances in that exact same way. But the way I should imagine this metric rho is going to determine a family of orospheres.
So what's the assumption sigma then?
For this particular set, I should say at least this sigma to be convex. But this type of construction will make sense for any metric. There are finer restrictions if you want the given metric to give you an embedded or immersed object. But at least I will try to illustrate how just solving this problem, it has only an algebraic solution. There is a little bit more to do in order to know if the object is going to be fully embedded or immersed. But solving the developing problem is actually a little bit more easier than that. So I'm going to try to exhibit that.
And so say that the conformal metric is just the metric on S2. You just you fix a metric on S2, say that rho is exactly S2.
That will give you back the origin.
Then the orosphere is always the one that touches the origin?
Yes.
And then say if instead of being the round metric on S2 is 100 times the round metric, it's a large constant times the round metric on S2, then what happens to the horosphere?
It will give you a sphere.
I know, but it will not go through the origin.
It will not go through the origin. It will be a sphere centered at the origin, and it may be either parametrized inside out or normally, depending if you multiply by 100 or you divide by 100.
So this is like a normalized distance to infinity, or to the point Z in some way.
In a way.
Okay, yeah.
So now again, it's important for us to understand construction because picking a canonical equidistant foliation might be a hard problem. If we are able to relate this as a one-on-one unquote problem with picking metrics in a given conformal class, we have a lot more techniques to pick those. So that's why we want to understand this type of construction.
So you go from the metric to the surface?
Yes. So let me.
Could you explain that?
Sure. I'm about to do that. I'm about to do that. At least I will explain how to obtain the formula. There is a direct way of giving the metric to obtain the formula. It's really straightforward. But there are some conditions about how to assure that it's embedded in immersed, and I'm not going to deal with them right now too much. But so I'll explain that. So in order to make this easier, I'm going to change the parameters I'm dealing here. I'm going to define t as the signed distance from the orosphere to the origin. And by this, here I have my copy of S2. Here I have my orosphere. And let's say my origin is here. There is a hyperbolic distance between those. And I say signed because I'm going to go with the convention that if the origin is an interior point, it's going to be negative. If it's the other way, it's going to be positive. In all these calculations, I have tried to be careful keeping track of signs. But if there is something wrong, then there is a plus or minus constant that will make everything correct. You define this parameter, and then moreover, you actually modified it to deal with this number. this is now useful because now you have the following parametrization for the Euler sphere at C with a given metric rho. This can be parametrized as follows. So remember, like an Euler sphere is just a sphere that happens to be tangent to S2. So I'm taking my input in S2 and mapping that into R3. This x point, this is just C. It's just being called another variable because we're about to take some derivatives in a second. So you need to be mindful about that. This R number is a number that you defined before. And again, Y is just your parametrization of the sphere. And it's a little exercise that this sphere that you're parametrizing is the Euler sphere you were trying to look at.
So in what is the parameter you could wrote H0?
Aha, this is the Euler sphere tangent at C by the given metric rho.
And what is R?
R is given by this formula.
So, but then R depends on T.
And R depends on T, T depends on rho. You could imagine that this R is a specific function depending on rho. So we have this parametrization here in particular. So what does it mean in order to have an enveloping map? Good.
So could you remind me again?
Sure.
Where does rho? So what's the relation between R and rho?
The relationship between R and rho is it's a little bit contrast to follow, but rho is going to fix an Euler sphere. That Euler sphere is going to have certain distance, and that will give you the R.
The Euler sphere, and that doesn't.
And that gives everything else. So now, an enveloping map is going to be given by an enveloping map goes as follows, or the term of an enveloping map is as follows. You need for each point C, you want to pick a particular point in your Euler sphere. Right, so this function alpha is the function that we normally aim to solve. It's going to be enveloping when what? When the tangent plane determined by this map corresponds to the tangent plane by the Euler sphere. Good news is that at Y, the tangent plane of our particular Euler sphere is the orthogonal complement of Y. That's just because we chose Y to parameterize our sphere, and then we know that the position vector determines tangent point in that following way. So what happens now with the tangent plane to this particular map? So let's take some derivatives of this in certain direction, multiply by 2 to make my life a tiny bit more easy. And this formula should now look like this. So this is what corresponds. All I'm doing is taking some directional derivative from this formula.
So what's,
Okay.
sorry, what's alpha of C?
Alpha of C is, because for each Euler sphere, you need to select one point in that particular Euler sphere. And that's what the function alpha is doing.
Right. So how do you
That's what the calculation is trying to get at. So then, in order, this is the tangent space of the Euler sphere, and this will be the tangent vectors of the map. Since you want it to coincide, you want all this term to be orthogonal to y. But these ones, you already know they are. That's by the same principle of at the given point of an order sphere, all the tangent vectors, which are the derivative in terms of y, are already orthogonal to y. So now from this condition, you just need that this inner product with y is equal to 0. Well, here you can go back and forth between Euclidean and hyperbolic inner product because they are conformal between them. So now this equation is just going to become that system of equations, right? For my particular case, you should have two directions. So now solving the enveloping map problem will just mean, in particular, solving this equation up here. So now, one sad news is that this problem has a not trivial kernel, but it's generated by is one-dimensional. I won't bother giving you this. You can calculate explicitly in terms of the coefficients what the kernel will be, but it's just a linear algebra problem, and to verify it's only one-dimensional. And the second observation is that y equal to x is a solution, because we already had one enveloping map to all the order spheres, which was the S2 itself. Right? By all construction of all of our order spheres was already tangent to this one. So now how do we find y from this information? Well, we can always pick some mu distinct from 0 real constant such that y equals x plus mu, the generator of the kernel, has norm equal to 1. And this will give you a explicit formula for
I'm sorry.
Sure.
What is capital X? So E is in the Heuristics, right? What about Y?
But what about which one?
E
Aha.
is E a parametrization of the horosphere?
E is a parametrization of your enveloping map. So what your enveloping map is doing is for each point is looking to the order sphere and then it's picking a point there. Right? But that point shouldn't be chosen just at random. The property of the enveloping map should be that the tangent plane to that enveloping map should coincide with the tangent plane to your order sphere.
But E belongs to the horosphere.
E belongs to the order sphere. Yeah.
How about Y? Because you say add Y.
Y also belongs to the horosphere.
Yeah.
Y also belongs to the
It's
horosphere.
confusing.
Yeah. It's
But as Z changes, so Z will as Z changes, the order spheres keep changing, right?
the order sphere keeps changing. Yeah. The bottom line is that when you compare the tangent planes, when you just pick any function, which in this case is alpha, and you compare the tangent plane with the tangent plane of the order sphere, you end with just an algebraic equation that you know explicitly how to solve, and you already had a solution, so you're able to find your desired solution.
But what
This,
is capital X?
oh, capital X, that's another part on Epstein paper that's a little bit confusing, but this is just another name that Epstein chooses for just the value C.
So I think what he's doing is he has a two-parameter family of order spheres indexed by the Z,
Mm-hmm.
right? Two parameters, complex number. And then in these two parameters family, he wants to pick an element, a curve, where if you look at the tangent vector to the curve, that's always perpendicular to the horosphere in which the guy is lying. That's what it seems to me. Yeah. Is that correct?
Yeah, that's more like what you're doing. We're trying
The
to.
horosphere is rolling, and he picks a point, and then the curve is always orthogonal to the other sphere precisely.
So it's tangent.
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 That's right.
Yeah, I mean, yeah, I know.
It's forcing the point on the curve to move it precisely. Yeah, that's right. It's tangent. Now, what's the relation with sigma?
What's the relation with sigma? Well, so the good part of this is that, well, we knew that from objects we'll go to metrics. The good news is like now from metrics we can go to objects.
Okay.
So now we just are going to reduce the problem to pick a specific metric in a given from a class. Before that, let me highlight one property, because here the formulas are quite explicit, which is the following.
Oh, got it. So your surface now is the image of V.
Aha.
Okay.
So if initially we have a metric rho, and this will give us an open set, and this will give us a embedded surface, if we just multiply that rho by a fixed constant, what it's doing is moving orthogonally t units with respect to hyperbolic metric. This could be easily just observed once you write down what the formulas do. When you multiply your metric by that, you see that what the map is doing is just moving orthogonally t units. So let me now describe the relationship.
The normal map, got it. The normal deformation is just scalar.
The normal deformation is just homogeneity.
Okay.
But now, in particular to this type of construction, we have the following. If we take where now the metric here is defined as a function of t, then you have the following formulas. So the aim of all these formulas is to understand a little bit more the relationship between these embedded objects and the metrics on them with this metric at infinity.
And this metric rho is defined in all of S2?
This metric rho is defined on open set.
On an open set?
On an open set.
It's blowing up the boundaries.
Blowing up everybody,
The metric in the embedded metric is the one blowing up at infinity.
No, the metric rho is defined an open subset of S2, right?
Of S2. Yeah. Oh, if you go to the boundary of that set, you mean? Yes. So now, when you start going by the normal flow, these are the evolution equation for the metric. When you look at the evolution of the second fundamental form, you know that at some point you need to do some exchange of covariant derivatives, and that will give you a curvature term. You take the advantage that you know that the curvature tensor for hyperbolic metric. That's why you get a factor, a delta factor over here. And with a little bit more work, you can also calculate the second derivative of your second fundamental form. So why are these formulas useful? Because here you should observe, if we would just be dealing with real functions, this tells you that this function should be written in terms of e to the t and e to the 2t. Or if you wish, hyperbolic cosine and hyperbolic sine. And similarly, because the derivative of g is in terms of h, then there is a similar statement for g. By doing that, you could determine the following. The metric g at time s is going to be the metric g at time 0, hyperbolic cosine plus hyperbolic sine of b0 applied to x, and the same expression applied to y, whereas your second fundamental form is going to be given as follows. So again, you should see to these formulas and the reason for these hyperbolic sines and coses appearing, because that's more or less the two general functions that will solve this differential equation up here.
What is B0?
B0, where I should declare that B0, this is just the shape operator
Initially.
at initially, yes, at time equal to 0. So this not only allows you to calculate how the principal curvatures are going to evolve, but also tells you that the frame that diagonalizes the shape operator is going to be invariant under parallel transport.
So S goes with S in time.
S is the time in this particular case. Did I switch it? Sorry. I think I might have switched it minusly to t. So here, all the s's should be t. Apologize for that. Yeah. All these are just the parameters in time.
Okay. So the principal curvatures initially should be strictly less than 1, no?
Yes, for all this formula is in general whenever for an epsilon is small enough. But if all the principal curvatures are between 1 and minus 1, as you point out, or if all of them were going to be positive, which will mean that we have a convex body, all of this will make sense as long as we go in the correct direction. So now what's going to happen? As you keep increasing here the time, you will see that your surface starts approaching the infinity. You see that your metric is going to start blowing out exponentially, and now you want to cancel that out to see the real relationship between the metric in the conformal case in S2 with the embedded metric. So now what's going to happen is the following. You should imagine this to be equal to your rho. You will have a metric defined at infinity and you'd have a sort of second fundamental form in the following way. What it is saying is that this metric rho will be the limit of the metric as you send time to infinity if you rescale them by this exponential factor. which you could just see from multiplying exponential in that set and just taking the limit. Analogously, that's not going to happen with your second fundamental form if you try to rescale it by exponential, because if, for example, you have curvature between -1 and 1, that's going to stay all the way. So when you multiply by exponential, that's going to 0. But you can calculate this gap between these two metrics, and that's going to give you a symmetric tensor defined at infinity. It's going to come up important to us in a second. So now I'll just recall you. We have, as again, delta meaning variation. The variation for the W volume was calculated as integral in the boundary of variation of the second fundamental form, variation of the metric against the metric dA. You could use these two, here this should be just 0. You could use these two terms to translate both the metric and the second fundamental form in terms of information at infinity. If you do that, you have lemma, which is the new variation formula. Here should be -1/4. Which alternatively could be written as follows. So there is nothing new happening in this formula except that you can rewrite these tensors in terms of these other two tensors. So now you could notice let me have your picture here. So this is M. The right set is a boundary at infinity, the boundary that we don't have set of manifold. And here we have N. So we can take equidistant copies of this, going bigger and bigger. The metric is blowing up exponentially, but if we rescale this by this factor, we will reobtain a metric in this copy of the boundary of N. Well, here, this boundary of N, where you're doing this calculation, should be this wide boundary of N that you have here. This boundary of N that you have is being done at infinity, but there is the identification that the normal geodesic flow is giving you. And you should see that the normal geodesic flow is going to be a different thing between these two manifolds, and this one comes equipped with its first a second fundamental form, By taking these limits, this one over here comes equipped with its metric and its second fundamental form there. So there is right now one gap to notice, which is normally here, in order to determine your object, you will need both the metric and the second fundamental form if you wish to reconstruct it. But from the construction of conformal metrics, if I have the conformal metrics, in particular, I have the embedded surface. But I know in order to capture an equidistant copy, I only need to multiply by metric by a fixed constant. So technically, in order to reconstruct all the foliation, I only need this metric. While here, these two tensors might be seen as a change of variable, you have actually all the information captured in just the metric. I could, and I will, condense all of that by doing the following. Let me say that if you here identified S2 with compactification of the complex plane, we need to pick a metric which is conformal to the flat one. So that's just the flat metric times some factor. If you will go to the process to construct the manifolds, calculate the metrics, and in particular calculate what this limit will be, which is what we have been calling the second fundamental form at infinity, the formula for this tensor is going to be given as follows. In coordinates, is going to be calculated as this, which we just do a mindful recalling of this as this. This Laplacian is calculated in terms of the flat metric, and this is the traceless part of your form. So it's reflecting a little bit more for us that all the information that we needed was just the metric at infinity to carry out all the construction. So let me see. I think this might be a good point to have a 5-minute break. Let's see. Couple remarks is going to be now, if we have rho, a conformal metric of the boundary at infinity of our manifold, then we can define the W volume of rho by just simply noticing that this that's going to be an equidistant family, if that construction makes sense. And we knew how to calculate W volume for those. So the key point is when this will be an equidistant family or not. The answer to that is that you can always take S big enough such that the map defined by Einstein is actually going to be an embedding. And moreover, in order to rescue the definition for renormalized volume, is now we have a W volume defined for AB metric representing a conformal class. So we can just take the metric of constant curvature to represent it. So which consequences brings that up in terms here of our variational formula? Here I should point out that H star, this is just a trace with respect to I star of the second fundamental form at infinity. And this is just the traceless part of the second fundamental form. Because of this formula, you should observe that the trace of your second fundamental form, this term is going to be traceless. This is actually the 2O term we have there. The trace of this term is exactly the curvature of your metric. Once you try this factor, you should obtain an e to the minus phi Laplacian of phi. So in particular, another remark is that H star is going to correspond to minus the curvature of your metric at infinity. So this is useful because now, if we are going to calculate variations of renormalized volume, well, we are picking metrics with constant curvature equal to -1. So then H star is just going to be the function equal to 1. So this term is not going to appear in our variation. We're going to, in particular, just have integral of the variation of the metric paired with the second fundamental form. And all of this should be at infinity. Yes?
Just go over again to the definition of renormalized volume. So that's W of what?
Is W of the hyperbolic metric in your conformal class.
Of the conformal class of the conformal class of what?
So what you have here is the following. So once you have here, here you have M. Here you have your boundary at infinity. You have a well-defined conformal class there.
A constant cut, that's right. And you pick that one.
And you pick that one.
But is n determined from the choice? I mean, the starting hypothesis.
This is determined with the starting hypersurface. What?
The n is how do we find n?
Oh, in this particular case is that when you have a conformal metric, you might not be able to define n, but you might define your equidistant foliation when it's very close to the boundary. That's going to depend on those conditions of if your curvatures have the appropriate values for them to be defined or not. So the foliation is only well defined when you are really close to the boundary.
Okay. And now you do a variation with respect to that hyperbolic metric.
With respect to the hyperbolic metric.
Conformals. You perturb the metric at infinity, and you see out there.
You perturb both, yeah. You now fixing for each conformal class, you're fixing the hyperbolic metric. Now that you perturb the conformal class, you're perturbing those metrics. And for that, this formulation is nice because now we know that this is just the function constant 1. So then that part of the variation is not going to appear for our calculations. So now what do we need to understand is how the hyperbolic metric changes as we change our conformal class, and how does that pair versus the second fundamental form at infinity that we have its formula given by this tensor.
In particular, to make sense, a neighborhood of infinity is mean-convex then, the principal curvature.
Exactly. As you get closer and closer to the infinity, if they're getting to closer to 1 or minus 1, depending where you put the sign of the normal vector. But yeah, that's the whole point of all this foliation only being well defined for large enough values of S. So that happens. First, first remark is by recalling that the formula of this is given by so what happens here? When we take the covering map for M, this boundary component, in particular in S2, is going to have an open domain associated there, where now your metric is going to be defined equivariantly. And in particular, you have fixed the hyperbolic metric in that. What is a way of doing that? Well, you know this is a simply connected domain, or we work in the case of where we know that's going to be simply connected. Hence, you know there is a map from the unit disk by uniformization. In the unit disk, we know how to define the hyperbolic metrics. In particular, by taking push forward, we know how to define it over there. By doing that, this, if we define this map as F, this is just going to be minus the real part of a quadratic holomorphic differential, not as Schwarzian. So let me define you as that. Assume that you have a map from an open set from the complex numbers to the complex numbers, which is locally univalent, meaning that f prime is always different from 0. You can define the Schwarzian of f as follows. This map is defined and used for the study of univalent holomorphic functions, and in particular has the property that this vanishes identically if and only if f is the restriction of a Mobius map. So what is the problem here? The problem here is that this map, as we have defined it, is only defined in a covering of our boundary, and our metric has a certain equivariant property, so you need to understand how that affects the manifold. How that affects this particular function, and in order for all this to make sense equivariantly, you need to pair this with a DC square. So why is this useful? Well, it's because, in particular, if we look to this defined as the Teichmüller space of a surface, you can identify the contangent space with such forms. In particular, I don't want to give too much details, but the bottom line story is the following. If we model the tangent space by just real part of quadratic holomorphic differentials, then the variation of the metric has a nice formula. So here, our vector v is going to be a real part of a quartic holomorphic differential, and then the variation of the metric is going to be exactly V plus something that is conformal to the metric. So the useful part of real part quartic holomorphic differentials is that when we want to vary the hyperbolic metric, there is a factor which is conformal to the metric, and here there is the traceless part of it. The good part is like this factor V is exactly what appears there. So let me take that as a fact and recall you that this is an orthogonal decomposition, right? Because we're taking the trace and then the traceless part. So then, when you take variation of renormalized volume, is equal to -1/4 integral over the boundary of. Here I should write variation of I Here's the fundamental form of infinity. You should remember this is a traceless tensor. So when you're taking the product with this, you can just replace this with V, since this inner product is just going to be 0. So let's see. And here should be, if we vary this in the direction of V. Then you could use this to look at the following proposition. If n is function, let me give a second to define this formally, but let me just give you the Hessian of renormalized volume in the VV direction. This is going to be equal to 0. The Hessian in the V minus V direction, this is going to be 1/8 integral of the boundary of M. The product with V. So this is telling us the spectral decomposition of the Hessian of renormalized volume.
So, and is it a critical point? If it's what are the critical points for the renormalized volume?
Mm-hmm. Of course. So function is going to be one of them, and in the other cases, the calculation is also going to reduce to this case. But in particular, here you have following. You should observe that from this variation, both V and this eco-fundamental form, they live in the same finite dimensional space. So then you know that for a critical point, this should vanish identically, which in turn, given the definition, this will mean that the Schwarzschild of the map F should vanish identically. Right, because we're concluding for this holomorphic quartic differential, its real part needs to vanish identically. But if the Schwarzschild vanish identically, we know it needs to be the restriction of a Mobius map. So in particular, when we see a critical point for renormalized volume, all these regions, they are not only going to be topological disk, but they're going to be honest disk, honest round disk in the sphere. So how this relates to a function manifold? Well, function manifold is going to be obtained as follows. Here you have your copy of H3, and recall that we have a copy of H2 inside of it. we can always collapse that H2 into a Riemann surface and use those isometries as isometries in the global H3. What's that going to give you is going to give you a manifold M, which is going to be your surface times the real line. And because you use this specific construction, the conformal class top and bottom are going to coincide with the Riemann surface you fix. In particular, here you could see that these domains being round corresponds exactly to that Schwarzschild completely vanishing. So now what happens? Because of the variation, we have the following. At a critical point,
so in the Fuchsian case, can you compute the renormalized volume? Is that a closed expression for that?
Yes, for the constant we had been picking for the Fuchsian case, we're picking it for exactly being 0.
0, 0.
Meaning, since we're picking the hyperbolic matrix at both ends, that's going to be the same with starting with the surface here at time 0. So that's going to give you a nice equidistant foliation where all the surfaces in between, they're all going to be umbilic, converge to hyperbolic, and you have 0 volume in there.
And say that we just move now the conformal class in one end.
Mm-hmm.
What happens to the renormalized volume?
Needs to strictly increase because of this.
Got it. And is renormalized volume always greater or equal than 0?
Because of this result, we'll know this locally to the Fuchsian locus. And after a continuity result, then now we know it in general. So yes, it's always going to be positive for the Fuchsian one.
And if it's 0 only in the Fuchsian case?
It's 0 if only if, yes, it's Fuchsian case. So yeah. So in this particular case, before getting to all that part, if you take this variation of here, you should obtain the following. Here you have derivative of v, derivative of w, in terms of this, because once you look at your variational formula, derive that in terms of w, since you know this tensor vanishes identically, the only part of the variation that you care is going to be exactly this one. So now you're going to know the Hessian in this case as soon as you understand what is the variation of this second fundamental form. So now this first variation is the easy one because because what happens? Remember, for a Fuchsian case, our only agreement was that the conformal part top and bottom, they coincide with each other. So if we take same variations top and bottom, we can take them while keeping our examples to be Fuchsian. So then we know the normalized volume is going to be constant to 0. So then that whole derivative should totally vanish. So we only need to understand the variation in the orthogonal complement of that. So now, shall imagine this is your Fuchsian manifold, and now let's take a variation v for the top and minus v for the bottom. In that case, will you differentiate your second fundamental form? This is exactly going to be equal to minus 1/2 v and minus v, which in turn gives you the second result. So that's telling you that if you imagine, since here now our Tecmuller space is going to be a product, if we perturb along the diagonal, we know that the value of renormalized volume is going to stay constant 0. But if we look along the orthogonal complement of that, we know this is going to increase to a positive number. So now what happens? Does the behavior of critical points that are function, what happens with your critical points? I should say theorem. So myself, and done in parallel by our techniques by Morianu 2015, which is if M is a critical point, but not function, then it is a strict local minimum. Simple proof of that is as follows. Well, how are the other critical points? The other critical points are going to be as follows. For them, there is going to exist a compact manifold N in the inside such that the boundary is going to be totally geodesic. This will mean that if we take the covering associated to this particular surface, we will see here a function manifold. So now what happens? This construction occurs in general, except that this part, we are not always going to have a totally geodesic end, or an end with a totally geodesic leaf. So in general, this is just going to be quasi-function, and has the property that if we had here in the boundary a conformal class C, then the top boundary component is going to have that conformal class, but there is another conformal class appearing in the bottom end, called by sigma C, and this is usually known as the skinning map. It's kind of like a hiding conformal class that you have once you take that covering. So now, once you try to take a second variation of renormalized volume here, you could use that you already know how to do that for the quasi-function case. In this particular case, it's going to happen as follows. If we take the Hessian of renormalized volume in directions v and w, this is going to become equal to the following expression. You have this formula because if you perturb C in some direction v, then the bottom part is going to be perturbed by a vector that is given by the derivative of sigma. Hence, you have this decomposition, and you just use these formulas in there. So once you know that, in order to produce the result, it's just going to follow from observing that this is a positive definite. Well, how do we do that? There is a result of Macmillan in 2000 that said that this map in this particular point is a contraction for Tecmuller metric. Now, this Tecmuller metric is a Finsler metric defined in Tecmuller space, but because we know that this sigma appear in the formula of our Hessian, we know that can be diagonalized. And now that we know it can be diagonalized, this result is telling us that every single eigenvalue should be strictly less than 1. So putting all of that together, this Hessian is strictly positive definite, given how the computation of the eigenvalues got there.
So I didn't get the beginning.
Sure.
How did you find that total geodesic guy? Why did you? I didn't get that part.
How do you find? Oh, well, that just comes again from this construction, from this fact. Once you have a critical point, you know that all of that is reduced to seeing those totally round regions at infinity. When you see all those totally round regions and you do all the Epstein construction for embedded surfaces, what you reconstruct is a geodesic plane. Yeah, but for all of that, was important for us to understand that these two land in the same space. So let's see. So in order to tell you the next part and answer Andrea's question, let me tell you the following theorem. Okay, this is self and also done by different methods by Bridgman, Brock, and Bromberg. This is 2017. Should be as follows. Well, the infinite renormalized volume is going to be computed as 1/2 the following quantity, where remember that M is the interior of a compact manifold with boundary. This is just the double of such manifold. And this implicial volume comes from, for 3 manifolds, you have a decomposition by compressible tori such that each piece is going to be either sci-fi fiber or finite volume hyperbolic. If they are sci-fi fiber, you ignore them. If they are finite volume hyperbolic, well, you will calculate a bunch of volumes, you add them up, and that's how you end with this quantity. In particular, if the double was a finite volume, if the double was a closed hyperbolic surface, sorry, a closed hyperbolic 3 manifold, this will just be its hyperbolic volume.
So that's the infimum over what?
This is the infimum of all G hyperbolic metrics in M, and I should say here with exponential ends.
So does your theorem relate to any kind of uniqueness of critical points?
Yes, that has to do. Moreover, well, in order to answer that, the uniqueness for critical points comes from, because of this comment, you know that for all of those, you at every end should have a totally geodesic leaf. And for those ones, it's already known that they either are Fuchsian, meaning they are just the product of a surface times the real interval, or they behave like the one that we just described here, which are acylindrical. So you know that they're like, it needs to be one or the other. And what this result,
I'm sorry, the infimum among all metrics equals 1/2, and then what is the VS, the event? Could you say that again?
So for a general 3 manifold, there is a decomposition along incompressible tori, such like each piece is either finite volume hyperbolic or sci-fi fiber. If it's sci-fi fiber, you ignore it. If it's finite volume hyperbolic, you capture that volume number and then you add it up. I can also let you, this can be also calculated in terms of the Gromov norm. You can just calculate the Gromov norm of your manifold, and that's going to be the same up to a constant.
So why you put D of M? Why not just M?
Oh, because this is the double of M.
Ah, got it.
So that's important. So how does this relate, for example?
Sorry, well, let me guess.
No, of course not.
Is the inf a min?
Is the
A min?
in the cases when you have a critical point, yes.
But in general, just pick some.
In general, no. In general, no. So,
Examples where it's not achieved.
exactly. So let me just, as an example, tell you this formula in the two cases that we have here. So if M is Fuchsian, this is M, the double of M is just going to be M times the circle, right? We have M versus times a segment. We double that, we're just going to get.
So what is the dimension of M?
Oops, sorry, that's my bad. M function is a surface times the real line, and the double is going to be the surface times S1. So in this particular case, when M is Fuchsian, when we take the double, this is going to be in particular sci-fi fiber, for which this value is going to be equal to 0. And that makes sense because the renormalized volume for this value is 0, and the manifold that we're capturing here has trivial simplicial volume. For the other cases, when M is a cylindrical, well, what happens for those? For those, remember, we have an exponential big N, and here we have a manifold with a totally geodesic boundary. So the double of M has a hyperbolic metric, meaning because instead of doubling all of M, we double this little chord that has totally geodesic boundary. And that's going to give you a manifold with a nice defined hyperbolic metric. You could see that in this particular case, renormalized volume was the volume of this little chord, while the simplicial volume, well, is going to add up those volumes 2 times. So that's exactly the proportion that we have here. So what is lacking? We know that these are the only critical points, and we know that the formula is satisfied for both of them. What else could happen? Well, what could happen is that as you change your metric, trying to achieve the infimum, you could be leaving the parameter space. You know, if you converge within the parameter space, real standard is going to be a critical point. You understand the picture. So what else could happen? Let me tell you that.
So in both cases you described that the inf is achieved.
It is achieved. So let's see. Let's do so how does the degeneration could occur as we take a sequence of manifolds? So let's just take Mn such that the renormalized volumes of these ones goes to the infimum of renormalized volume. So basically 3 things could happen. We could have an interior geodesic whose length is getting smaller and smaller and smaller. In that case, in the limit picture, and I'm going to call my limit picture M infinity, that really close geodesic, that really small geodesic, is going to become a cusp. It's going to have a neighborhood, which is the product of a tori times the real line, where the size of the tori is getting exponentially smaller. These ones are OK because these regions are finite volume. What else could happen? Well, maybe the curve that is getting really, really small is in the boundary. So for example, let me take this boundary component. We could have a curve here, which is getting arbitrarily small. So when this goes to the limit, it's going to become a node. Well, here, this little neighborhood is going to become this little neighborhood. So this could happen in your limit picture. And the third occurrence could be as follows. Well, maybe the curve that is becoming really, really small has different homotopic representatives appearing on more than one boundary component. So what will happen? Well, since they are all homotopy, you're going to be able to connect all of them. In this particular case, a little bit easier to say because it's just going to be a cylinder. In the more complicated cases, you could imagine there's a bunch of cylinders coming along a common curve. So at this particular situation, your limit could become disconnects. Meaning you could take base points either at one side of the cylinder or the other side. You will see many different components. But in the limit, the picture you should have should be more or less like this. So let's see. So this cylinder here is going to give you a punctured torus in this case, a punctured torus in this case, which are going to correspond to this one. So this is the circle representation. And this other side, this punctured tori with this punctured tori, this whole cylinder is getting cutted and collapsed. And it's going to give you this different component. This could give you potentially different disconnected components, or could just be cutting and still preserving the number of connected components. So after a little bit of work, first of all, these three things could happen. And moreover, it could happen in as many quantities as they do. So once you show that happens, well, you first of all prove a continuity result. Meaning, if we take the limit of renormalized volumes of Mn, this is equal to the renormalized volume of M infinity, where this should be taken into account as a possibly disjoint sum. And we need to take into account that now we're dealing with boundary component that has cups. But all of our procedures still works in those cases. You need to prove such a limit. So let me give you a quick heuristic why such a thing should be believed based on the following. This is an alternate definition of renormalized volume. So by volume, we will just like to integrate the function 1. Right? But in this case, that is not possible. Well, we could take a function rho, raise it to the c, when now rho is just a function from your manifold to the positive numbers. C is just a complex parameter. If this is defined as a meromorphic function, we could take its finite part at c equal to 0. So this will mean that's going to be a meromorphic function. It's going to have expansion along 0 that's going to look more or less like this. This integral level around 0 is going to look like this. And this is the finite part that you capture. So there is a result saying that renormalized volume could be reformulated as this. But I need to tell you something special about the function rho, because not any function is going to work. And it has to do with the following. First of all, this condition should be satisfied. This is equivalent to saying that the level set of rho corresponds to our equidistant foliation. And the second condition is going to be if we take the product of rho squared with the metric g, this actually makes sense in the limit at infinity, coincides with the hyperbolic metric at infinity. Right, so again, it's the same problem of how to renormalize an integral procedure, and then how to make a decision which one is the one that we distinguish. There's a complete parallel between those. So why is good this formulation? Because this is pretty much a PDE in a way. Here is your equation that you need to satisfy close to the boundary, and this is like your initial conditions. Moreover, this type of PDE, you can solve it by method of characteristics, and method of characteristics are good because if your equations converge and your initial conditions converge in a compact set, then you have enough good convergence of your solutions, and enough good convergence of your solutions might give you the enough convergence that you need for these integrals to show such a limit. So what do you know? If we take now continuity into hand, then we know that M infinity needs to be a critical point for renormalized volume. And the idea of this is, remember that M infinity was obtained by a sequence going to the infimum. If it wasn't a critical point, then we will be able to perturb our sequence a little bit to obtain a lower value. And for that, we are using continuity not trivially. So then M infinity needs to be a critical point for this. This means that each component is either function or a cylindrical, where I recall you, those are the two cases for which we know this equality held. So how do you do in order to produce a minimum for renormalized volume? Well, you just need to cut along enough cylinders, do maybe some drilling, maybe some pinching, up until each component looks like that. And you calculate the renormalized volume in those limits. For which I will end this saying that for which one, we'll just call this one, is true. There is a little note here, which is we will need to be able to reassemble the formula at both ends. Right? We know that the infimum of renormalized volume corresponds to the renormalized volume of this, and we know that the renormalized volume of this is equal to this formula, but that's only true piece by piece. We don't know that if all of that is going to be true putting all together. So what could be the problem? The problem could be that, and let me maybe just so let's start in this picture. Let's take double of each component. This cylinder, once you take double from both components, that's going to be a dividing tori, which are the tories that you use to decompose this into many components. So the cooling cylinder seems to be OK. But what happens with, say, this pinching curve that we have here? Once we double that component, that's going to become a run to cusp. It's going to look locally like this. And the problem for those is that when we take the double of the original m, we have that filled in. So there could be a gap there. Similarly, if an interior curve was being drilled, when we take the double of this component, we're going to take two cusps appearing, one per copy. And that's also going to be a distinction with this formula, because this formula is considering then with them fill. The bottom line is that if you fill a cusp, and this is a result mainly done by Thurston, is filling a cusp decreases your volume. So if you do this procedure, and then in some point you end doing a drilling or doing a pinching, you could get less volume here, but not doing that, and just restricting yourself to cutting cylinders. So in particular, the note here, by that, is that one does this only by cutting cylinders. So in particular, if you take an example of a hyperbolic manifold which is non-cylindrical, where there could be not 3 cylinders and a different example for a function one, then we know we need to cut along one of the cylinders in order to obtain this minimum. I will probably finish this yet to give the appropriate credit, is that this type of procedure was done for the Shockey case by Guillermo, Mariano, and Rocha. At the point of then, and what they're doing is just adapting their proof that works more generally for this case. Just to be that clear. And yeah, I think that's the proper credit.